Hello, on behalf of Mozilla Research, I'd like to introduce the RR tool to you. So RR's goal is to be a drop-in replacement for GDB. So you'd use GDB approximately, or use RR approximately how you currently use GDB in your workflow. But as I'm going to try and show in this little demonstration, RR has some advantages over GDB that can make your debugging process a lot more efficient. So let's introduce RR's features by showing it on a very trivial contrived program, which is actually one of the RR tests. So what's annoying about debugging in a traditional debugger is the non-determinism of execution. So you may reproduce a failure in one session, but you find that you missed some critical bit of information that you needed. And then you try and replay it again, or run the execution again, and you miss that the failure doesn't manifest. So you don't get your information, and you've just wasted your time. So what R does is it lets you record this non-determinism so that you can replay it deterministically later and debug that deterministic recording. So on this simple program we have here, we dynamically allocate some memory. We're going to launch a few threads here. The threads will all race to this printf statement, so there's non-determinism in the thread schedule there. They'll get through the barriers, and then they'll all race to this done statement, and there's more non-determinism there. And so we can see this if we just simply run the program. So do that a couple times. Okay, so you see we have a certain thread schedule, we have a certain address space. We run it again, we get a completely different thread schedule, and we have a different memory layout. So this is a real problem for debugging, because if your failure is dependent on either of these sources of non-determinism, then you may not reproduce it on the first or the second run. So let's show what happens with RR. So how does RR do this differently? So in the first phase with RR, then we want to record the bug that we want to take care of. So in this case, I'll just go ahead and get this going. So you see I got a certain thread schedule, and I got a certain address space running under RR. So let's try again. And you see I get a different thread scheduling and approximately the same address space. This is for a reason that we won't cover here. But now I've recorded the failure that I want to debug. It manifested on this particular recording. But the great thing is that entire execution is saved to this trace. So by replaying the saved trace, I can make that same failure happen over and over again. And since we're working with this contrived example, let's continue on imagining and say that the failure was a crash at this free of this data. So something went wrong with that free call. Now we see that we have the printf statement right before that free call is made. So that's a good place for us to start debugging, to attach our debugger. So what we're going to do right now, we're starting in the second phase of our debugging, which is the deterministic debugging phase. We have our trace, and now we're going to run some queries over the trace. So the first thing we're going to find out is where is a convenient place to attach. So what I just told the RR replayer to do is to mark all standard I/O writes with some information that's useful for debugging. So this first number is the PID of the process that made the standard I/O write. In this case, we only have one process, but if we had multiple, then we'd be seeing multiple PIDs here. And then the second information is the recorded event at which this write was made. So it doesn't really matter how those events are defined, but it gives you a unique identifier that you can use to attach the debugger at that event, which I'll demonstrate here. So -g means play up to this particular event before attaching the debugger. And so you see that's what happened. So we replayed some of the execution, and then RR launched GDB and attached it. So skipping over execution is very useful if you have some commands or traces that you don't want to run over a large part of the execution. You just want to skip to a particular point where you care about to reduce the noise or improve the overhead of the recording, or excuse me, of the debugging process. So now that we're in GDB, we have almost its full command set available to us. So we'll go ahead and set a breakpoint here where we wanted to examine the free call, and of course we only want to do it if it's the thread we care about. Okay, and with this breakpoint set, we can continue as we normally would in GDB. And now that we've reached the program point that we care about, we can examine the state. So I can look at the backtrace, I'll look at the data variable, and I'll look at the register file, just as you would in any other GDB session. So now our debugging process, we've just found the ultimate effect of the bug, and now we want to work backwards toward the cause. So let's say again in our contrived example that by examining this free call, we suspect now this set thread name call. We think it may have done something to cause the free to fail. So our next step is going to be breaking on this for the thread that we care about. But we've reached kind of a problem in traditional debugging, because by the time we got to the 3 to examine it, we've already run the set thread name call. The only way we can get back to this is by restarting the execution. But if we restart the full execution, then it's going to give us another non-deterministic result. So the bug that we're trying to diagnose right now may not even manifest again. So this is really our strength. So what R does is it co-ops this run command for GDB, and instead of restarting a new non-deterministic execution, it just restarts another deterministic replay session for the same trace. So you're going to see the same thread schedule, all of register contents will be the same, all memory addresses will be the same. And you can optionally pass it a event number to start from. If you decide that you missed some program state that you needed to examine earlier where you skipped in the previous run, then you can correct that by passing it to event. Okay, and so let's see what happens when we do this. So we restart it. Okay, and so we hit the breakpoint that we just set, except as I tried to emphasize, we hit it for exactly the same execution that we saw in the first instance when we were looking at the free call. So now everything's exactly the same, we're just looking earlier in the program state. So we just made a step backwards in the causal chain from the effect to the cause. And this is a silly enough example that we won't pursue it any further, but if I wanted to, I could continue to make these backward steps by setting breakpoints earlier in execution and then just restarting execution to reach that earlier breakpoint. And across this restart call, this run call, all of the other debugging states stayed intact. So my first breakpoint is still there, I can hit that. And if I want to restart again, then I'll hit my same breakpoints with exactly the same memory addresses in the exact same way. So this is a very basic example of what R can do. We're using a contrived program to introduce it quickly and emphasize R features over the actual debugging itself. But in the future, we'll be showing you some much more interesting examples with a non-trivial program, Firefox. So thank you very much.